Alright, so we're looking with operations with vectors in 3D, and it's a lot alike to the stuff we did in 2D. But giving you a couple minutes to try these, but let's go ahead and run through some answers here. Someone want to give me an answer to u plus v? Julia?
Negative 1, 14, and 3.
Good. Negative 1, 14, and 3. 3 plus a negative 4 is negative 1. 8 plus 6 is 14. And negative 2 plus 5 is 3. Okay, so notice you're doing the same stuff you did with the two-dimensional vectors. It's just that third component. Okay? How about the 3u minus 2v? What did you guys get for that?
17, 12, and negative 16.
Okay. Anyone else get that?
I got 17, 6.
Okay. So we got a couple of different answers. Let's double check here. So 3u, we would have 9, 24, and negative 6.
Oh, no.
Okay. And then be careful when you're subtracting. If you do the minus 2, if you distribute a negative, then we would have vector addition. If you distribute just the 2, then you keep the subtraction between them. The key is just make sure you only do the negative once. Alright, so if I distribute a negative 2, I'd have a positive 8, negative 12, and negative 10. Okay? So 9 plus 8 is 17, 24 minus 12 is 12, negative 6 minus 10 is negative 16. So we were correct. The original answer there. Okay? Alright, someone want to give me the magnitude of u that you got? Matthew?
Square root of 77.
Square root of 77. Okay, so you had 9 plus 64 plus 4. You had 3 squared plus 8 squared plus 2 squared. By the way, when you do this, especially if you're punching into your calculator, you know that when you square it, it's going to be positive. So don't bother even typing it in. All that does is open the door for you to accidentally hit a button wrong or not have parentheses quite right and mess it up. You know it's supposed to be positive. Or better yet, you know what 2 squared is, so just plug in a 4. Okay? So yeah, we have square root of 77. So then 5u, what's the magnitude of 5u equal?
5 surely.
Yeah, it's 5 times the square root of 77. Remember, our magnitude of a constant multiple is just the constant times the magnitude of the original vector. Okay? And that's what I wanted to get at here with vector w. If you notice, vector w has, the 3 components have a common factor of 24. Okay? You might have seen 12, but either way, you would see that we could write this as a multiple. I'm going to write this as 24 times the vector 2, negative 3, and 1. And I don't know about you, but when I go to find the magnitude of w, I'd much rather do 24 times the square root of 2 squared plus 3 squared plus 1 squared than have to actually square 48 and 72 and 24. My numbers stay a whole lot smaller, and notice the simplest radical form will be a lot closer to simplest radical form here as well. So notice we get 4 plus 9 plus 1. That's going to be square root of 14. So it's simply 24 root 14. And that's our magnitude of w. Okay? So you see here, if you see a common factor like that in your components, you can factor it out to keep your numbers a little smaller if you're going to find magnitude or that. Okay? By the way, remember dot product worked that way too when we get to dot product on Thursday on Thursday. Okay?
It's the same, right?
It's the same idea. Yeah.
You add another.
Okay? Now, a couple other things I want to address here, working with our vectors thing. And this is not exclusive to 3D vectors, but we can use this here. You can do different algebra with your vectors. For example, if I wanted to solve for what vector v was, I could do the algebra just like I would back in pre-algebra. I'd subtract 3u, okay? And I would have 2 times vector v equals vector w minus 3 vector u. The one difference is that we don't have division. Okay, we have scalar multiplication, right? So what should I do here to get rid of the 2? We don't have division. Multiply by 1/2. Okay, and I know it does the same thing mathematically, but just to be proper here, we would multiply by 1/2. So v is 1/2 w minus 3/2 u. And now we know what v has to equal. Okay? This would be the type of thing where we know one vector and we know what we want our result to be, but we don't know what that other vector would have to be. Okay? So, we can solve for it. Here, similar idea. We'd start by multiplying by 1/5 on both sides. So I'd have a u minus v equals 1/5 w. I'd subtract the u from both sides. So now I have a negative v equals 1/5 w minus u. And now I can multiply both sides by a -1. So v would simply be a -1/2 or a -1/5 w plus u. Okay? So it's not too hard. It's just a little bit of algebra. We just have vectors. Okay? But you could treat them just like you would other variables and stuff. Okay? Questions? Okay. 2 other things I wanted to address here. Okay? Finding a vector with a certain magnitude in a given direction. This is something we've already done in 2 dimensions. The concept is the same. If we wanted to get a unit vector, remember we simply multiplied the vector by 1 over whatever its magnitude is. If we wanted to make it have a magnitude of a specific value, say k, we would multiply by the magnitude we want divided by the magnitude we have. Okay? So, in this example, if I wanted a unit vector parallel to 12, 10, 6, the first thing I would do is find the magnitude of 12, 10, 6. So 12 squared plus 10 squared plus 6 squared.
Wouldn't it be better to find out the angle if you want parallel? It doesn't matter if you
Well, here's the one thing. In 3D, there are multiple angles at play. Is it the angle off of the x-axis, or off of the y-axis, or off of the z-axis? There's actually 3 different angles that we could use here. So this is where this is particularly helpful. Okay? You're right, in 2 dimensions you could have just found the angle and work with it that way. Okay? This one you can't. Alright? So the magnitude of our vector is this. So 144 plus 100 is 244, plus 36 is 280. So square root of 280. Alright, and square root of 280 is, let's see, that'd be 4 root 70. Or no, 2 root 70. And that's 2 times 35, which is simplest radical form. So that would be just 2 root 70. So if I wanted the unit vector then that would be 1 over 2 root 70 times 12, 10, 6. Okay? And of course you would multiply that in. You'd get 12 over 2, which would be 6 over root 70, 5 over root 70, 3 over root 70. We should probably put this in simplest radical form. So that's going to be 3 root 70 over 35, 5 root 70, well actually no, that'd just be root 70 over 14, and 3 root 70 over 70. That one won't reduce at all. You guys know how to simplify radicals, I just did it pretty quick. So, okay? Now, now that my magnitude equals 1, if I wanted the magnitude to equal 10, I'd just multiply that whole thing by 10. If I wanted the magnitude to equal 50, I'd just multiply that whole thing by 50. Okay? Or I could, if I knew that from the beginning that I wanted the magnitude to be 50, I could have just multiplied by 50 over 2 root 70. And that would have gotten me there all in one step. Okay? So that's the difference there between these two formulas. But we saw that when we were working with the two-dimensional vectors. Okay? Does anyone not understand something I did there? Okay. Last thing here, vector addition. Okay? Vector addition can be a little bit tricky when we want a certain result and we have our vectors written as points. Okay? This is something that'll show up a lot, so I wanted to make sure that you guys understand this. We have 3 points here, A, B, and C. Okay? When you draw it, it's not too hard to figure out, okay? But notice, if I want vector AC, I have vector AB, and I have vector BC, okay? When you draw it, it's a little easier to see that AC equals AB plus BC, okay? Here, though, is the key, even without the drawing. Notice, think about these vectors as directions. I want directions to get from A to C. Well, this gives me the directions to get from A to B. So now I need to get from B to C, right? This only got me to B. Now I need to get from B to C. So I need to go from B to C. So if I do A plus B, or A to B, and then B to C, that'll get me from A all the way to C. Okay? So again, think of it like directions. Drive from here to point B. Now that you're at point B, drive from there to point C. And you will have gone from A all the way to C. That will be the end result. Okay? The key is, look at that point that they have in common. And make sure that your start and where you end is correct. Okay? Getting those correct is really important. Okay? Also, because you may have been given vector CB instead of BC. So to get it to work out right, you would need to take the negative of that. Okay? The opposite. To get the letters to work out right. Okay? So, Now, once you've figured that out, it's an easy problem, okay? Vector AC, AB plus BC is just 1 plus a negative 2. So that's a negative I. Negative J plus J is 0J. And then K minus 3K is a minus 2K. Notice here you don't have to put in a plus 0J. If you want to, that's fine, but you don't have to. Okay? But that would be our result AC. Okay? So that was our last thing that I wanted to look at, just to make sure that you guys understand that. Again, these first couple lessons, I know we're hitting a bunch of kind of different things in each lesson, but we're laying the groundwork, making those connections with what we've done before, and also laying some more groundwork for as we get into more advanced concepts with our 3D vectors. Okay, so it's important that we understand everything that's going on. Okay?